And the next speaker is Srikant, who's going to talk about properties of TD learning.
Thank you. So this is a joint work with Lei Ying, who is supposed to be here, but he's running late. So I think most of you here know what reinforcement learning is. At a very high level, you have an agent that takes an action, which affects the state of a dynamical system. And then you get feedback about how the state was affected, as well as the reward and cost. And of course, we've all heard about great applications to video games, board games, autonomous driving, assisted driving, and so on. In the context of, to pose it as a Markov decision process, you have a dynamical system. X is the state of the system. The state at time k plus 1 is a function of the past state, the past control action, and some randomness in the system. And the cost is an infinite horizon cost. Here I'm assuming discounted cost for simplicity. And the problem is to find the optimal control action as a feedback policy. In other words, you're interested in a feedback policy to minimize the cost. And traditional MDP literature solves this using value iteration, policy iteration, linear programming, and so on. I'm going to consider a simpler problem here, which is just simply one of value function estimation. So here we are fixing a policy u, fixing a policy mu. So uk is mu of xk. And we are simply interested in evaluating the value function. So VFI is basically the cost that you incur starting from state I to infinity. And this can be, as is well known, it can be written as in the form of a Bellman equation. So if you can solve this fixed point equation, you know V. But this requires the knowledge of the dynamical system. So in other words, if it's a discrete dynamical system, then what you need is transition probabilities to compute this, to solve this fixed point equation. Of course, in machine learning or reinforcement learning, we ask the question, what if the transition probabilities are unknown? More generally, one may not even know what the state space of the Markov chain is, and the cost also could be a random variable. In particular, I'm going to assume that the state space is so large that one needs to approximate it in some manner to get a tractable answer. So I'm going to assume in this particular talk that the value function is linearly parameterized. So there's an unknown weight vector theta and a known feature vector phi I. And the goal is to estimate the unknown weight vector from a trace of the x's. And of course, a very popular algorithm to accomplish this goal is the TD learning algorithm. This particular version is called TD0, as probably most of you know. So what you do here is you look at what's called the temporal difference, which is the difference between the left-hand side and the right-hand side of the Bellman equation, and drive theta in the direction of the feature vector phi. Okay? And in the special case where the phi is just a vector of all zeros except for a 1 at I, then you get it reduces to standard tabular TD learning. Okay? So this is a well-studied problem. And one way to proceed would be to first rewrite it as a linear stochastic recursion. So one can write theta k plus 1 as theta k plus epsilon times some matrix A times theta plus some vector B, where the matrix A is a random matrix and the vector B is a random vector. And prior work in this area has shown that A bar, in other words, the expected value of A in steady state, that matrix is a Hurwitz matrix, meaning that all its eigenvalues are in the left half plane, or of the left half of the complex plane, and B bar is equal to 0. What I mean by centering here is that you would like to drive theta to some theta star, but just by recentering, I'm just going to assume theta star is equal to 0. Just I'm rewriting it, okay? Yeah. So the goal of the talk is to obtain finite time performance bounds. In particular, I'm interested in obtaining some expression for the expected value of the norm of theta k square. And we'd also like to obtain higher moments if possible, for example, norm of theta k power 4 and so on. And the motivation, a very high-level motivation possibly could be studying finite time performance bounds with fixed step sizes may lead to adaptive step size algorithms which may converge faster. I'm not going to touch upon this in this talk, but we have an ICML workshop paper where we use the results from this paper and came up with an adaptive step size rule, which actually performs much better than the best fixed step size rule or any diminishing step size rule. So you can have three types of rule where the step size is either fixed, or step size is like 1 over k power something, or actually adapt the step size as a function of what you've observed so far. And I'm talking about the third type of algorithm. And we have some results on that that are interesting. There's a number of recent papers in the last few years, and here's probably an incomplete list of them. The main difference in our work is that we assume that the Markov chain X is a Markov chain, and additionally, we don't project theta into a compact set. On the other hand, some of these papers also derive stronger results in terms of they also study more general algorithms, such as what happens if you use averaging, use a fixed step size, and then, for example, this paper by Lakshmi Narayan and Chibaswari, for example, studies the impact of averaging on the answer. So we don't do that. We just simply, in this particular talk, I'm just going to talk about you just output theta as you observe it, and the adaptive step size algorithm, we do more. So the main result is that expected value of theta square has a geometrically converges, and in steady state reaches something that's of the order of epsilon times tau, where tau is the mixing time of the Markov chain. And the second result is that if you look at higher moments, if you look at the moments of theta square, for example, then up to moments of the order of 1 over epsilon, you can get an expression. For moments larger than 1 over epsilon, the steady state moments are infinity. It's kind of interesting because if you think about it, you might mistakenly think in the limit as epsilon goes to 0, you get an Ornstein-Uhlenbeck process, and of course you might think that the theta has a sub-Gaussian tail, but this result suggests that it doesn't even have an exponential tail. The proof of the main result is a drift analysis. So you find a right Lyapunov function, consider its drift, and show that the drift is proportional to WK, but with a negative sign, okay, a plus some small constant. And the Lyapunov function that works is a standard Lyapunov function people use in control theory. In particular, if you study a differential equation, this is called the well-known ODE method, where you study the differential equation associated with the evolution of the linear stochastic recursion. And it's well known in linear system theory that the natural Lyapunov function that one uses to study this is of the form theta transpose p theta, where p is the solution of this Lyapunov equation. So the main difficulty in our analysis is that when you study the drift of this Markov chain, of course, the Markov chain becomes closer and closer to the differential equation only in steady state. So if you study the drift from one time step to the next conditioned on the previous time step, it doesn't work. So you have to condition sufficiently in the past so that x reaches, or x is close to steady state. And much of the paper deals with analyzing the above drift by conditioning way in the past. And for the higher moments, you consider the same Lyapunov function, but raised to the power of m to get bounds on the mth moment. In particular, you also need expressions for all the previous m minus 1 moments to get the answer for the mth moment. So in conclusion, we obtained finite-time bounds on the performance of TD learning and related algorithms. The results also work for anything that can be written in the form of a linear stochastic recursion. And based on this, we also have an adaptive learning rate selection rule. This is in addition to the Lei Ying. There's a third author. The first author of this paper is Harsh Gupta. So I presented it at an ICML workshop. And we can also extend these results to two-time scale stochastic approximation using what is called singular perturbation theory, which is a theory for studying ODEs when there are 2 time scales involved. That's it. Thank you. Fixed step sizes. So, but our analysis also holds for decaying step sizes. So we have a appendix where we analyze finite time bounds for decaying step sizes. But what we found.
Using the ODE method with fixed step sizes, that sounds tricky, no?
No, it's not. Yeah. So we just use the ODE method as the motivation, but then we study the drift carefully. So much of the work is in trying to get this expression exactly. Yeah.
And next up,